everyone, I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy journalist for over 20 years, and I like to bring you behind the scenes interviews with the people actually working on the missions that are going to carry humanity to the stars. Joining me today, we've got Michael Amato from NASA Goddard. Michael, welcome to the show.
Thank you for having me.
So, who are you? What do you do?
I have a unique job, I'd say. Most of what I do is I'm a manager and lead engineer of the planetary and lunar line of business, we call it, at the Goddard Space Flight Center. So, long story short, I do a lot of things, but I develop the missions, choose some of the missions, work the technologies for those missions and the early designs, and then we propose them. We compete for a lot of our missions, and DAVINCI is an example of that. And we go through the proposal process and the design process, and I do that for the missions, for the instruments that are lunar and planetary, and sometimes even stay a little bit with them in implementation. But it's a broad job, and I love it, I have to tell you.
So, what are some examples of some missions that you've worked on in the past that people might be familiar with?
Well, from Goddard, you might be familiar with Lucy, which launched recently. I worked on that for years. Might have even interviewed a few people from Lucy at some point. Met Maven, worked on in the early stages of that. Had OSIRIS-REx, which not too long ago, at least in my mind, made the sample at Bennu, which I still watch the video of that sometimes.
I saw that one launch. I was actually at Kennedy Space Center for the launch of OSIRIS-REx.
I was down there too. I think, it's one of the things about my job is interesting is when you're in the room and you're creating a mission with the PI on a whiteboard or sometimes even a piece of paper, and then you get to see it's a long time from that point through the vetting process at Goddard, and then the vetting process through step one proposals, and then the vetting process step two proposals, not only just to start the mission, but then to get to the back end where that thing you were trying to design 6-7 years ago is actually working, launched, and you see it touch the asteroid. That is it is an exciting experience, but I guess a lot of people would believe it takes that long, but not a lot of people are involved from that very early seeds of a mission to the actual implementation.
Well, I mean, at this point, you've been through enough missions that you've seen the whole process soup to nuts. I mean, I think about some of the people who are proposing some of the more far-flung missions. I mean, I think about the folks at New Horizons who had to wait 10 years for their spacecraft to fly to its destination. People talking about, the interstellar probe that may take 20 years to get out to the point they can actually start doing its science. As we explore further afield into the solar system, that time frame, like you can be a new PhD and be nearing retirement when it's time, finally time to see your science. It's such a long process. You're lucky. Venus is so
typical.
Close.
Yeah, that's common. Our job, especially when I start so early on these missions, you have to think about not only the your far future, but also other people who will come behind you and finish a mission or analyze the data. If you don't think long term, I mean, we build these missions, it takes 4 or 5 years, but that's the core hard work of finishing the design and building them and launching it. But if you're designing to a target that's far away, which is typical, we have limited energies and it takes time, and some of those missions like sample return take a long time to get the sample back. You have to really be thinking about the future of our exploration, not just your career.
Yeah.
Some of these missions don't happen until you're going to be either gone or doing something else, or who knows.
So how does this start? Like when we think about, we could rattle off dozens of missions with interesting targets. What is the very inception of an idea for a space mission? Where does it come from?
Well, it could come from a lot of places. I mean, I'll use DAVINCI as an example since we're talking about today. In DAVINCI's example, you might know this. I think a lot of your viewers would, that especially in planetary and lunar. Now, I do some human exploration work, so it's not totally true. But for the science missions, they are driven. The ideas, the answers are driven by the decadal. We just got a new planetary and lunar decadal released not too long ago, weeks ago, literally, and there was a previous decadal. Those questions, which the community works through and then prioritizes, those questions beget ideas. And there's a lot of ways to get at some of those questions. Missions can't answer all the questions, even for a particular target. And based on your area or your organization's skills or the instruments you've worked on or the subsystems you've worked on, and usually we're highly partnered, so it could be a university scientist, we'll have discussions. People you know, people you don't know will talk. And usually we have a large number of missions that could go after even a certain targets like Venus's questions. But in DAVINCI's example, we were actually originally after the New Frontiers proposal, the larger Venus in situ mission, the New Frontiers. And that proposal was a combination of a radar and a probe. And that was our first attempt to design a probe and competed. And I thought we had a unique approach to those science questions. And that mission proposal a long time ago was not selected, became through an iteration of the design, the earliest DAVINCI proposal. But that was really a discussion how to best get at the in situ questions. What kind of hardware, what kind of mission design. It's a complicated discussion because a lot of it has to do with your experience in costing, your experience in scheduling, your experience at risk, and putting together the subsystems. And those ideas can go together on a whiteboard in a series of meetings and slides pretty rapidly over a couple of months. But then the details of what you can actually board and propose and the risk take, it literally does take another year or so to create kind of that mission concept to propose.
Yeah, like from my perspective, sort of watching it from afar, I sort of see two separate groups. There's the people who, like the scientists, the planetary scientists, that are they're asking the questions, and they're, when you read the press releases and things like, we've discovered this gas, but we wish we knew more. We don't understand this. A lot of the time is like, scientists are often obsessed about the things that they don't know, the questions that they have. And so they've got these questions without an answer that are sitting out there sort of, I don't know, haunting everybody. And then on the other hand, you've got the engineers kind of going, hey, I just thought of a cool way that we could try to answer this kind of question or that kind of question. And you'll see them give talks at conferences and so on. And I think they obviously are like part of the decadal survey. As the decadal survey starts to plant some flags, you get these two camps starting to cross-pollinate and kind of going, I've got an idea for that. Well, that would answer my question about this. And then it starts to gel into some kind of spacecraft that then is too expensive and has to be cut down into something more reasonable.
You're feeling the story of my life. Well, I would say this. What I try to do in my job is I try to make that a little more integrated. We'll target the science questions and have an idea. And usually these early science questions, those scientists, if we're good at our jobs, are linked to those engineers early on, even before they might have the idea. So what I try to do is not link an engineering solution to a science question, although I do an awful lot of that. I try to make sure we can create the engineering solution actively for that science question and for that scientist. So it's a little more proactive and a little more integrated. And we try to not make those camps, right? We try to make that one team. And some of the large organizations like a Goddard or a JPL or even an APL and some other centers too, have the depth in both science and engineering to integrate those teams. And hopefully if we're doing our jobs right, those engineers know those scientists, even ones from universities for a long time. And people have a feeling for what instruments you're good at, what subsystems you're good at. And I like to not make them camp so much as an integrated group of a community which talks to each other. I mean, the decadal is driven mostly by scientists, but you're right. There are engineers involved. We run a lot of the studies for the decadal, the pre-studies and the during study here at Goddard, and JPL and APL do a lot of them too. And so even in the decadal process, there's an awful lot of engineering involved in exploring how to solve those questions, because some of the decadal missions go after things. You have to have a proof of concept to know where to put those questions in the context of the NASA program, which is part of what the decadal does.
Yeah. Camps, I guess it feels to me like I can see people floating ideas in both directions, and it's more like they cross pollinate. That I see the engineering ideas that might work. I mean, I think of things like a star shade, like this idea of a star shade, which has been proposed now for probably 20 years or so, is starting to pop up for ground-based observatories and space-based observatories, and in small versions and in large versions. And there's this kind of engineering going on that's looking to try and maximize the chances of it being able to answer science questions. And it's interesting to see both the questions and the ideas to solve them are getting refined, and eventually they can sort of come together into metal and silicon and actually and propellant. So let's talk about DAVINCI then. What is the, you mentioned previously the Venus in situ probe. So what was the original idea for the larger version?
Well, the larger version, the new continuous version, was trying to combine, the radar maps. Venus it's covered in clouds; you can't see through it. Radar is the only way, really. If there are some windows in the near IR, but one of the few ways to get really good maps of the surface. And that concept early on was trying to combine that surface mapping, the surface altimetry, what you can do with a radar, with that in situ confirmation, that real confirmation of what is in the atmosphere. Together, that made a complementary and quite capable mission. I mean, and in fact, now we essentially have a flavor of that bigger mission, because both DAVINCI and Veritas were selected as separate missions. So, it's weird how things come around, but we will essentially, DAVINCI will be the second launch, Veritas the first, but in a roundabout way, we have that earlier mission now with two great missions going to Venus right after each other. And so we have that combination of data we can leverage.
I'm sure that comes up a lot where you're like, we can't do this. Oh, well, here's an idea. And what do you know? It's also better and also fits within the new mission parameter. I kind of wish we'd thought of this first, but it's the constraints that help us further and sort of clarify our thinking, which happens to me all the time.
Yeah, constraints and competition will drive really good decisions. And sometimes, you can't predict how these things work out, how the mission's selected, nor can you predict what you might have to change in the design even after you're selected. But sometimes I think, as time goes on, you end up with really good and sensible solutions. And this combination of missions, I have to tell you, is going to be very powerful. And we're going to hear a lot about Venus in the next 10 years, largely due to these two missions. And the combination of the two is going to give us some results that I don't think people have seen before.
All right, well, let's talk about the mission. So what's the, break them down however you want. What are we looking at?
All right, well, I'll just, describe DAVINCI at a top level. I think everybody, based on our discussion of the past 5 minutes, has a flavor for, or a sense for what it is. It is a Venus mission. We combine an in situ analytical probe with some sensors on the spacecraft, and we're trying to get after, we're using what we think are the right instruments to get after the highest priority measurements in situ. I mean, but broadly, we're after, the origins of Venus, whether it had oceans, the boundaries of habitability, what's the history of the atmosphere? And those are the big questions. And there's really 3 flavors of those questions. There's atmospheric and origin of the evolution. How did the atmosphere evolve? Can we back out its history? How is it different than Earth? Why is it different than Earth? How does it compare to other analogs, either exoplanet analogs, how does it compare to Earth and Mars as a combination? What are the surface properties? Was there an ocean? What do the tessera look like, which is where our probe's going down? How do they compare with other highlands? There's a lot of questions that even just the probe goes after, and that was kind of the guiding principle when Jim Garvin, our PI, and a group of people, we got together and made these missions. The probe mission is a result of those goals, and I think the combination of the probe itself, which is the core of the mission, and the 2 sensors on the spacecraft make for a pretty powerful mission.
And so what orbit will it be taking? Because you say in situ, which tells me it's going to be tasting the atmosphere, ideally.
That is the core of the mission. All right, let me back up. So we have a spacecraft. It carries the probe. There's a probe flight system, which we call the entry system, and the probe together. The probe itself, what people think of as what goes in the atmosphere, we call the descent sphere. Literally, is a sphere within the probe. We launch. So I'll walk through the scenario, and you kind of get what we're doing. We're not in an orbit around Venus, and what we're doing is flybys. So we launch in, I think now we're the second launch. So we're in June 2029, and we do our first gravity assist in January 2030. What we do in the gravity assist, we use our 2 spacecraft sensors. There's Visor, which has UV and near IR capabilities, and a Tech Demo, which is Qubits, which is a compact UV invisible spectrometer, a new small using freeform optics and onboard AI to kind of demonstrate how to build it small. Those 2 sensors will be doing the work during the flybys, looking at the dark side, inferring things about the surface, looking at the UV absorbers, which are an unknown. We'll do that in both flybys, doing some pre-work for tessera in general. And then on the third flyby, the second flyby is November of 2030 right now. And then the third flyby is 24 months after launch, 2031. And that third flyby is when we drop off the probe. And the probe will enter about 24 or 48 hours after release. It encounters the atmosphere at about 145 kilometers, and then it does a 1 hour descent we could talk about in more detail. So there's two flight systems, the spacecraft and the probe system itself. And we actually, right, the second at least, are not in orbit, that baseline. We do have the capability to go in orbit, but that's going to be a pet quarters of whether we do that. But we do a lot of our spacecraft science from multiple flybys, and then the last flyby we drop off the probe.
Okay, so you're doing these flybys, and I'm assuming a bit of a gravitational assist while you're at it as well. So after that flyby where you drop off the probe, what happens to the spacecraft? Is it going to come back for another flyby, or is it done?
It can. There's a lot of options in the spacecraft. At the point after the probe release and we get the data back, the primary mission is done. So there's a lot of options for the extended mission. You're probably familiar, and your viewers are. You probably hear about these extended mission proposals. And any mission, including DAVINCI, has to go through a proposal to extend its mission after the prime. And there's a lot of science that can be done with DAVINCI after with future flybys and other options. And we'll have options we propose to NASA probably even before then, and they're aware of them. But right now, our primary mission is done. But yes, there's stuff that could be done with DAVINCI after that last.
And so theoretically, it could go off to some other target, do a flyby of I don't know, Mercury or search for Venusian Trojans or whatever. The point being that all of its science is going to be done during the flyby, kind of similar to, say, New Horizons or Voyager, when the Voyagers went past Uranus and Neptune, that the science is done then.
Yeah, like I said, we have an option to go into orbit, which NASA has an exercise, and we can do that. But right now, we're doing the flybys. The benefit we have is we have multiple flybys, so we have to come back.
Yeah.
Getting to Mercury would be a tough one. The spacecraft designed primarily for the core mission. Most of your viewers, and I know that Discovery is a cost cap proposal. So we really do customize a design for the cost. So we're not really over designed for the mission. So within the capabilities, our limit is to what it could do after the primary mission.
All right. So I'm not going to put words in your mouth. But if I understand this correctly, you've got a primary mission. You can do a couple of flybys. The spacecraft should theoretically be in perfect shape, of course, because of the way you've engineered it. And it can then go on to do other things, such as do another flyby of Venus and perhaps even, I don't know, use aerobraking or something to maybe insert itself into some kind of final orbit. Who can say what the future holds? But we know what has been defined for the DAVINCI probe. Is that?
Yep. And that's the core mission.
Understood. The core mission, right? And we look at missions like consider, say, the Spirit and Opportunity, right? They had a 3-month core mission, 6-month core mission. I forget, was it 3 months, 6 months? Anyway, yeah, and ended up working for 10 years. So the future, who knows what could happen? Okay, so you drop off this, and so during these flybys, you are scanning the atmosphere. You are trying to understand you mentioned a whole bunch of things there. So, what specific big questions about Venus are you hoping to answer, and how? So you talked about, how long has this atmosphere been around, and when did it have oceans, and so on. So how will you hope to uncover some of these answers?
Yeah, well, I think the best way to do that, let me go through the instruments that are on the probe, the core of the mission. Actually, I'll go through them all. But the probe is designed to survive the environment, which we should probably talk a little bit about. Actually, I'll talk about it now. That was one of the real challenges. I mean, on board, we have a VMS, a Venus mass spectrometer. It goes after noble gases, isotopes, atmospheric composition, trace species. And you can use those measurements to kind of bound the history of the atmosphere. And that's one of the few ways we can get back to what happened originally. We have Vtls, which is the Venus tunable laser spectrometer. It works with the mass spectrometer, the primary mass spectrometer. It's capable, it literally uses laser spectroscopy to go after water, oxygen, D to H ratio, sulfur species, potentially phosphine-related species. And it's really after some of the past history and current habitability. So those are the primary two instruments. We also have VASI on board, which is the Venus atmospheric structure investigation. As we go down, we're measuring temperature, we're measuring winds, we're measuring accelerations. And we also have VINDI, which is an exciting part of the probe. That is the descent imager. Once we're below the sulfuric acid clouds, we are going to be taking images of the tesseract we're going to be coming down on top of. And that'll be more images that I think that have ever been taken of the Venus surface. That combination of instruments really is the right set of instruments to answer the science goals I threw out at you earlier. I mean, it's hard to do some of that stuff, but we have a very good science team. That science team is very experienced in not only the models of Venus, but using this data to back out that stuff. And there's very few ways, except for being in situ, to really go after the history of a planet. And there's a lot of questions to answer. One of the challenges of getting those instruments to the surface, though, we can't, do those snips all the way down. And we are literally ingesting the atmosphere from, right after entry all the way to the surface. And it's a tough thing to design that probe. That probe has to survive. Near the surface, it's 90 atmospheres. It's 800 plus degrees Fahrenheit, 400 something Celsius. It's supercritical CO2. You're to get there, you're flying through sulfuric acid droplet clouds. This is not a normal engineering design situation. So we have a titanium probe with specialized seals and a specialized window, and a lot of what we've all done over the past many years is try to make sure we refine that design. So the point of that probe is to make sure we can make those measurements all the way down to the surface, and that probe is a unique thing. And those instruments are designed to adjust that sample and turn it into the right sample for the instruments. But that core data, which is sent up via a really kind of a unique adaptive rate comm system, which uses an S-band to kind of optimizes based on the return through the atmosphere. So we'll get a lot of data back. We'll get some prioritized data back. We are really focused on getting that core data back from that probe. And all of those instruments provide really core science questions. And this team, our science team, is very prepared and anxious to get that data back, because that's going to provide years, decades, maybe even of atmospheric data. And if we can back out the habitability, kind of try to answer that question, whether there were oceans, well, if there were, how did they go away? How do we get in that runaway greenhouse? I mean, how does that compare to other maybe exoplanets? We're bounding a lot of questions we don't have answers to. It's been, by the time we launch, it'll be 50 years since the U.S. has sent an in situ mission to Venus. That's really kind of impressive. It's our closest neighbor, and impressive might be one word. It's frustrating to some of us who are pursuing the missions. But that's a lot of progress in instruments. That's a lot of progress in engineering. That's a lot of unknowns and unanswered questions, which is why Venus was so prominent in the last decadal and this decadal. So, that's the engineering behind it, and those are the primary instruments. And you'll find this in a lot of missions. You combine measurements to go after a combination of questions, to put them together to get after a core set of science goals. And those are kind of, that atmospheric evolution, the composition, surface exploration, the history of Venus, and then the surface properties, surface chemistry, what's going on in the atmosphere right now, kind of giving us evidence of what's gone on in the past.
So how long will the spacecraft survive? I mean, I think about the poor Venera probes that the Soviets designed, and they literally just kept throwing spacecraft, figuring out how long it took them to die, made them tougher, tried again until they finally got something down to the surface. You, I guess, have the advantage of all of the data of their poor dead spacecraft to understand what kind of environment. So what do you think the journey is going to be like for the descent probe?
Well, we're designed. It's about a 60-minute descent. It's we're below the clouds after 30. We drop our parachute and that lower atmosphere is not only is the hardest thing in engineering to design to, as you pointed out. We have some knowledge from other sensors, which we're certainly using to our advantage. But a lot of that low atmosphere we're trying to get, not only is it the toughest thing for us to survive, but it's also where a lot of core science is. I mean, supercritical CO2 is an interesting soup to go through. That's kind of how it behaves. We're in a free fall at the end, and just to think about that, it's really more like a liquid. It behaves like a liquid, but that final 16 kilometers from 145 down is where 60%, 66%, I think, of the mass of the atmosphere is. And you think about that, there's a lot going on down there. But we wouldn't know quite as much about the temperatures and the pressures and the sulfuric acid if we hadn't had those Russian landers and, of course, pioneered Venus from the U.S. And because of the thermal environment, you're fighting. I do a lot of work designing these systems. You're fighting an unwinnable war against the temperature. You're fighting 400 plus Celsius of an entire planet with your little spacecraft, and you're going to lose that war. The question is, how fast do you lose it? And so we're designed to survive the pressure, but the heat really is what will destroy us. It's 60 minutes. We're designed to survive another 17. If we land and survive, we're not designed to do that, and we don't have to requirements. But that's our margin. We'll continue to get data up. But kind of on that theme of that core mission and discovery, we are designed only for that core mission. We'll do the 60 minutes. We get all of our level 1 requirements and all that data back up before we land.
Right.
And everything else after that will be. So I imagine our maximum survival time will be in that kind of 70 to 75 minutes. And then we'll just get too hot, even though we have some extended temperature capability. It gets hot really fast, and there's no fighting that war. And it's just too hot for electronics to work, too hot for us to send data back, too hot for the camera to work.
So even once you reach the surface, I mean, you're estimating like 17 minutes of survival, but you probably won't be able to get the data back out of the atmosphere because of the heat.
No, the 17 minutes is how long we stay under temperature to do it. So we should be able to get that data back. I mean, think about the surface survival, and I don't know how likely it is, but we're going to hit pretty hard, although we don't hit very hard. I think our touchdown speed will be about 12, 13 meters per second. That's like a low speed car crash.
Yeah.
We could survive, but we are designed thermally to be low enough temperature to theoretically get all that data back and have the instruments survive for another 17 minutes past that.
Right.
I don't know what the odds will do, but that'll be bonus size.
Yeah.
We get everything I described to you before we touch down. In fact, we change modes late to make sure we get the right kind of data back, and especially and near surface, we're looking after surface atmosphere interaction. Those temperatures, weird chemistry goes on. So we get all that done. That 17 minutes would be, I have to tell you, if we get that 17 minutes, that would be a real impressive feat, because that'll be a survivability on the surface. Now, our camera points down. In fact, it's one of the weak parts of the probe, so that window at the bottom will have to survive that impact. But that would be real fun. We will get that data back until we get too hot. Assuming we don't roll and are pointed away from the spacecraft, we should get a lot of that data back.
Well, that's what I imagine. I'm just sort of like, if you do get that signal back, then you'll see the thing sort of float down, hit the surface, and then roll around on whatever the terrain is. And then maybe, if you're lucky, people will be able to sort of stabilize the image and try to sort of get a better sense of what it is that it saw. With that, I mean, I'm sort of envisioning, right, that it starts out with a parachute, goes down to a certain point, and then this parachute just vaporizes, and then it falls. How different are those environments for the probe to have to deal with?
Yeah, it's different. I mean, we have our aspect interface at about 145. We have a pilot chute that comes out and it literally pulls the probe out of its entry system. It's a carbon-carbon entry system, which is how we survive that entry. And the pilot chute kind of pulls us out of that. And then the main chute deploys, and we're on the main chute. I think from about 70, I have to recheck that, but 70 kilometers, so maybe 60 through about 40, right through the clouds. Basically, the clouds are sulfuric acid. It's not as hot up there. There's been discussion, a lot of interest about how habitable is a cloud. It's not as hot. It's not as high pressure. What is the chemistry going on there? Could that be habitable, some weird life form? But we're under the parachute for that, and right as we come through the clouds, a little after that, we drop the main parachute. That is a tough environment to be through. It doesn't have to last very long in that condition. In fact, we're doing tests, some parachute material tests right now. And then we free fall. We're spin stabilized. We have spin vanes. We spin slowly. We should be relatively stable on the way down. The VASI measuring the temperature and the loads and the winds, and we're taking those measurements all the way right down to the bottom. But from below the clouds down, from about 40 down, we are literally in a free fall for what becomes a little bit of a soup, an atmospheric soup. So we're not. That's why we're landing or hitting. Now we're landing. The question is only how fast.
Yeah.
So
you're litho braking.
That's right. And but it is a thick, weirdly behaving atmosphere, mostly CO2, and so there is a lot of drag, and we have a drag plate, and we won't hit as fast as people would think from a free fall, because that atmosphere is so thick, and that's one of the reasons we're going. I mean, how do you understand how that atmosphere works? The chemistry, the constituents. We don't have a lot of data to confirm what's going on in that atmosphere, and just the features of the atmosphere that cause you to go down slow. If you just think of engineering and you're thinking about how you slow down, we don't even know a lot about the atmosphere, enough about the atmosphere to be totally sure how much we slow down or what the interactions are going to be. And we're going to get all those answers. We're going to be sniffing that atmosphere, taking those pictures, doing those atmospheric measurements and the load measurements and wind measurements all the way down. We're going to go off. And just our entry and drop itself will tell us a lot about how the atmosphere interacts. And these are going to be unknowns or things that aren't known well that we're going to have out of that. Just even thinking about how slow you go down and the environment we're going to learn about. When we get it, we're going to know where we were every minute, every second, and even that descent profile gives us science. It
is interesting to think, like Mars, it's so difficult to land on Mars. Mars eats spacecraft, and NASA is trying to figure out ways to try and scale up, even to do, like, say, a 3-ton payload to Mars, and that's like at the very limit of what is possible with an unpowered landing, and yet with Venus you literally just drop things into the atmosphere and they land at a reasonable speed. The downside is the horrible hellscape that they will arrive at that is going to try and tear your probe apart. It sure makes Earth feel like a great place. Like when you think about that, it's just kind of amazing how great Earth is.
The way I describe Venus to people, and you've probably heard other people say this, I'm deeply involved in some of the engineering solutions for Venus surface, but it's not a place for even the best engineers to design something to survive. It's not a great place to be. It's not a great place to design, even our probe. It's very, there are future Venus missions I think will try to land. There will be future missions that'll try to land and survive and take a sample in. I'm even working on those missions now. And those things have to survive longer than an hour. And we know how to do that a little bit, but not much, 6 hours. And just the sulfuric acid going through it, the weird chemical behavior of not just the supercritical CO2, but other things. But again, it's the pressure and temperature that really kill you in the end. It's a fight you can't win. And it's not a great place to run instruments. It's not a great place to take samples. But the fact that it isn't, and the planet is so similar to Earth, and yet looks like that near the surface. I mean, think about that. We're the same size. We're in the same vicinity of the solar system. And yet that planet looks completely different than Earth. I mean, it couldn't be more different. It's one of the most, as a matter of fact, it's one of the most extreme conditions in the entire solar system. Yet it's right next door. How?
Yeah.
Why?
Yeah.
What is going on there? That is why you do a mission like DAVINCI, and we'll do the best we can to design that thing to survive as long as we can. But there will be following missions. DAVINCI will be a precursor to those following missions, and those following missions that we I work on some of those technologies now. We'll work on that next set, but we'll know an awful lot more after DAVINCI to be able to design those things. And we'll know an awful lot more about its atmosphere and the history of Venus to be able to design that next mission once DAVINCI gives us our data.
I mean, it would be wonderful to find the smoking gun and go, oh, right, that's why Venus is so terrible. But the evidence seems to be leading towards it wasn't always so terrible, possibly even fairly recently, and the things that happened to Venus could have happened to Earth too if we'd had a bad string of volcanoes or a really bad asteroid impact or something. And so I'm sure the goal here is there's got to be some set of conditions that happened either in the chemistry of the mantle or something that stopped it from being able to have plate tectonics or something. And yet, as you say, it really is our twin in so many ways, and that could have been us.
Yeah, the reason we send this probe in situ, the reason you have to be in the atmosphere is so you can bound the answers. And probably a lot of your viewers know, scientists work in models. What could the answers be? And these models infer certain histories of the atmosphere and certain things like how much volcanism was. Did that play a major role? How did the surface form? Why is it spin this way? So all these things there's probably no one smoking gun. There's probably lots of small reasons that you end up in this totally divergent path. But if we don't understand those reasons of how a planet so close to us in size and distance can go that divergent path, there's a lot we don't understand about Earth. There's a lot we don't understand about solar systems. There's a lot we don't understand about planets and other solar systems. So we go to these instruments, we do the hard thing, we go to that horrible environment, with that probe so we can get the hard answers, and so we can bound the models. And if we get the right measurements, we can bound the history models, and we can give you, hopefully, the right 2 or 3 answers rather than the 5 or 6 or 10 that are floating around now. And now you can start to work backwards into what likely happened, which gives us insight into what could have happened to us if we were in a slightly different position or different things happened. But what did happen to Venus, what could happen not only in our solar system, but is probably happening in other solar systems all the time with planets of our size this close to a sun of our size, or at least in this kind of habitable zone. So you can't do any of that work or a lot of that work without actually going in the atmosphere. And that's really the core of DaVinci, is getting those measurements in that orbital environment.
You mentioned briefly the ability of the spacecraft to try to sense that the phosphine, which was, of course, that discovery a couple of years ago, fairly controversial, of a potential biosignature in the atmosphere of Venus. How well do you think you're going to be able to provide some kind of conclusive answer about the presence of phosphine?
Well, that's a good question. It's hard to say for sure. We'll be able to measure some phosphine-bearing elements. I mean, and in combination with some of the other things you measure about the processes going in the atmosphere, hopefully we'll be able to back out a lot of information that'll give us some information about what is going on there with phosphine and that process that processes that could create it and whether it exists. I mean, usually, how it works in science, there's a lot of indirect measurements that have to kind of inform you of the answers. And it is an interesting potential result, and we think that DaVinci will help inform some of that discussion going on around phosphine and how it could be there and whether it is there in the form that it appeared to have been.
So I want to speculate now. So I just want to, anyone at NASA that's watching this is, I'm now pushing this conversation into uncharted territory, and we understand that this is not what is planned for the existing DaVinci Plus and Veritas mission. What do you think it would take to keep a spacecraft alive longer on the surface of Venus?
Well, you're asking the right person that question. When you design missions, and I do all the targets, Venus is a struggle, and we look at landers for Venus. I have. I think, without getting into a minute conversation, we know how to survive the pressures. We know how to get the data back through that weird atmosphere. We know how to do all that. What it's hard to do, what's really hard to do for survivability, and we've done studies, you can see that, it's really the survival that does you in. And you can even imagine, getting energy from, that atmosphere reflects a lot of light. You can't even, but you could imagine even getting some power to survive longer. But the thermal environment is what's slowly killing us. You only have a few ways out of that. You can fight that thermal battle for longer. We know ways to do that. DaVinci itself uses, change materials, things that change state to absorb heat more actively. We have it. We have phase change boxes around sensitive components that extends their lives. Landers have to survive longer, 6, 8, 10, 24 hours. I've worked on those, have a lot more phase change material. They have a lot more thermal mass. There's an advantage to the way, some of those old landers now with just way too much mass and all that. Well, one of the dumb advantages you have is that thermal mass gives you time before you get too hot. The other way out of that problem is that you have to design, and this is very hard, electronics, not just simple electronics, but electronics that could survive the higher temperatures once you get there. That is a whole field. And it's, NASA's done some work to do that in very simple. There's some simple transistors and batteries that can survive that. And maybe you could do some simple things, but to do measurements like this that would really drive you to survive on the surface longer, you really have to solve that problem through the whole range of electronics. And that is a very difficult thing that would take decades to do. But that is one way out. You push the survival temperature of your instruments up, theoretically, all the way up. But there's some farther fetched ideas. You can use thermal cycle engines to try to, just like your air conditioner on a 100-degree day, you're fighting, or a heat pump more like, you're fighting that. You times that by many stages. You can imagine theoretical ways to pump out heat even into that hot environment. And so and with a big lander, but we're talking very big landers that are very complex and expensive.
So if you had like a big lander, like I don't know, like something that was multiple tons, and you had, say, a nuclear fission reactor on board to give you all the energy you could require, you could just keep pumping that heat out and try to survive as long as possible. But eventually that heat is just seeping in, and eventually it's going to melt every piece of electronics in the spacecraft. So in the sort of perfect world, how long, I'd heard like ideas of like using a Stirling engine and kind of running it in reverse. What is like the best case scenario, do you think, that a lander could survive?
Well,
using that method, using
that method, it could be a long time. The problem is that method doesn't exist. You have to stage it so much. You have to use a lot of materials, and we looked at this a little bit. You have to use materials. You have to change phase. You have to pump a lot of stuff out. You can't just go from your normal operating temperature inside the lander. You have to keep it at to pumping heat into 400 plus C. So there's multiple stages. That is a complex set of machinery that would consume a lot of volume, a lot of power.
Yeah, it's fine. You're using a Starship. It's fine. Don't worry about it.
Yeah, Fraser, you're giving me a nuclear fission reactor.
Mm-hmm.
You're
I gave you you get a kilopower reactor. You can take 150 tons if you want after we refuel your Starship in low Earth orbit. Right? What would it take?
I think smart people are going to figure out a way to keep instruments running for a long time. And I think those Stirling engines and those heat pumps are the way. One of the few ways out of it. They take power, but if you have a lot of power, there are theoretical ways. We'd have to do a lot of technology development. Some people have actually looked at it. That's the direction I would pursue. Now, I can't prove to you it's doable, but I think I would go after the combination of changing materials multiple times, venting materials, and then using stages of cycling heat pump like Stirling cycles to try to pump some of that heat out, make yourself more efficient by phasing materials between those and cycles. That takes up a lot of volume. You need we've looked at these things. You probably would surround the inside of your lander with layers. We already do this with insulation to protect us. You probably surround it also with layers of materials that would boil off and vent off, and then you try to cool them down, and another layer interface with another heat exchanger, and then you try to pump that heat out through multiple stages, which is probably one of the few ways to do that. But if you're giving me a lot of power and a lot of volume, which you are, you're very generous.
Yeah, I am very generous that way.
I think there might be ways to make something survive on the surface for a long time. And in that scenario, it wouldn't be hours or, we've imagined ways 2 or 3 days with normal, but a passive thermal survival techniques, maybe even using phase change materials, but much advanced versions and venting them out. We could go a week. But now something you're talking about, you could maybe in those conditions, because it's not as hot in the clouds, and so there's other flavor emissions that survive on balloons, floating in those cloud layers.
Well, we'll talk about that in a second. I just want to finish the ground first, and then we're going to talk about the atmosphere. So fine. I mean, months and months. That sounds great, but it is pretty complicated. So what is the state of those heat surviving electronics? Because we've reported on this quite a bit fairly recently. There's been some really interesting discoveries made by NASA and others running electronics in Venus level temperature for a long time. At this point, what remains to be able to be heat tolerant for the conditions on Venus?
Well, yeah, you're talking about LISI, the LISI team. They've done a good job, testing. I have a lot of experience testing in Venus conditions, and those tests aren't easy. The chambers you design and the test conditions, they've got some very basic electronics. They've been making stepwise progress through the most fundamental electronic sensors, through now the power sources. You could imagine doing, and in fact they have, imagined doing simple things like temperature for a long period of time, transmitting simple data for a long period of time. I mean, 6 months, because you can really operate, having power for that amount of time. The remaining challenge is complicated because you can't build a mass spectrometer or even a camera out of any of those electronics. You need CPUs. You need memory that is more complicated. You need all sorts of chips. You need optics that can survive those temperatures. You need, most fundamentally, most detectors can't survive of any type. So it's a very complex. I can imagine, decades of investment needed to make more complicated instruments. The good news is you can imagine very simple things like weather sensors being designed. And in fact, that's what LISI is. It's kind of the beginning of a weather sensor design, and that is useful data by itself. So I think it'd be a long time before we could build a camera or a mass spectrometer that could survive to those temperatures. But it may not be a long time before we have a long-lived weather sensor. And that's useful data. I mean, we're still trying to get long-lived weather sensors in various parts of Mars. We don't have, there's lots of reasons. You can even think about the lunar geophysical network. There's lots of reasons to have simple sensors placed at various points around a planet, driven by science questions. So I think those simpler things will be realizable, in the next 10 years. The more complicated things are going to do a lot more work. And it's because you have to work through a large series of an ever-expanding set of electronics and detectors to make any of those sensors work, combined with try to rethink those instruments, right? About try to join in the middle. So that's a lot of work, I think. But it might be a long, long time.
It does feel to me like there is a ton of spin-off technologies that can come from investigating a rethink on high-temperature electronics. That, having things that can work with jet engines or fusion reactors, or there's all these places where having a computer function at 400 Celsius would be helpful. And so it does feel to me like that's very valuable work to sit down and go, how do we design a camera when you think of every single piece, every single element that's inside the camera, and go, well, instead of glass, let's go with quartz instead of, right? That process has a lot of offshoot technology. I mean, I'm sure a layered heat pump Stirling engine has its value on Earth as well, but it does seem like a very fruitful direction to go. Okay, so let's talk about the atmosphere then, because again, you are falling down through the atmosphere, but what if you could stay in the atmosphere? How conducive do you think the atmosphere of Venus is for some long-lived balloon type mission that could stay aloft for a long period of time?
Well, I've worked on those missions. You'll see my name and a few other people's names you probably know on some of those studies. We know how to design those missions. And I wouldn't be surprised if the thing that comes, don't quote me because I'm one of the people who helps make these decisions.
I already warned NASA that we were now well into speculative territory. This is all on me. This is for an RFP that I gave you, not for right.
Yeah, I think that mission is a mission we know how to do. It wouldn't surprise me. In fact, I might be one of the people working on. In fact, I might already be working on.
Who could say?
Missions that and I can tell you, I really am. We really are thinking hard about what comes after DAVINCI and Veritas. It's one of my jobs. What happens in 12 years and in 15 years? And you do have to start now. That's how long it takes. And one of the most attractive missions, there's two flavors. One is a lander that survives longer and actually takes a sample from the surface to confirm what's going on, on the surface, the chemistry in the surface, what the surface is made of. That's one direction. The other direction is a longer survived balloon mission that goes around in the atmosphere high enough so that it can survive. And some flavor of those missions actually use the balloon to go dip down and dip back up again. Those are more expensive missions. Not all those missions are Discovery class. That might be more New Frontiers or even directed mission class cost. But I don't think we have to reinvent the wheel to do those missions. We probably use the same mass spectrometer versions we're flying on DAVINCI. Nor do I think we do. I think we have to reinvent the wheel to do those surface missions to ingest samples. I think we know how to do those missions within reason, with a lot of engineering challenges. But those balloon missions are interesting. You asked for the atmosphere. You can imagine those missions. We have preliminary designs for missions, and you can read about them. You can actually download some of the studies for those. And
I have. What kind of, what would one of those missions look like, do you think?
Well, the way I would do it, and I'm not, I'm just one opinion, but I would go strong after the balloons that could dip up and down. I think having that various altitude, being able to dip down where it's a little hot is important to get kind of that broad survivability. The only, we have to deploy a balloon after entry. That is not a simple thing to do, and inflate it so you don't keep going down. You have to have the package of payloads on a gondola underneath that balloon and survive and have enough power. You have to get the data back. That is not simple in a balloon mission because you have to go in orbit and then you only get so many passes because you're going in a direction at a speed the atmosphere is taking you, which we can predict. And so getting your communications back is one of the challenges, but I think we know how to do that with the right size spacecraft. That's what makes these missions a little bigger than normal, bigger than expect. But if you have the right set of sensors and you have a balloon that's dipping up and down and sensing what's going on in the upper clouds, the lower clouds, the upper atmosphere, you're getting a lot of good data over a long period of time. That makes it different. DaVinci is going to go sense those things straight through, but you get a dimension in those long-lived missions. It's probably one of the few things we won't answer with DaVinci because we go too fast. So, and that's useful stuff, because if you really after habitability, you can imagine that data being useful too. And you get a lot of answers about local chemistry, and you can theoretically in the gondola, we can answer some questions we don't answer with DaVinci. So I wouldn't be surprised if 12, 15 years from now, we're talking about surface landers that are a little longer lived, that are actually trying to dig a sample up and invest in and analyze it, or balloon missions that are spending longer time, 6 months, 7 months, 8 months in the atmosphere, going up and down so it can, cool off and heat up again, and getting into that habitability, I would call it, in that upper atmosphere.
Those winds, they're taking you all the way around the Earth every, 4 days or so, all the way around Venus, every 4 days. And so you get a really good view of the whole planet. And at those low altitudes, you're taking pictures, doing radar scans ideally of the surface. You're getting a really pristine view that we just I think about our current, the Magellan mission, what's the resolution, 30 meters? It's terrible. And to go and to get down to sub 10 centimeter resolution would be a game changer.
Yeah, Veritas will do better than that when it launches. The thing about balloon missions, and the thermal kills you again. So the way we've designed our thermal, you can dip below the clouds to get images, but you get hot fast even below the clouds, and you're also exposing yourself to those sulfuric acid droplets every time you do that. So the way I imagine is you would be dipping down for very short periods of time to take those images you're talking about, but then you'd spend most of your time at a higher altitude, because the thermal even gets to you at those lower levels, even in a balloon scenario. So you probably struggle to take pictures all the way around. You probably get little blips from different places as you go down, and that's even a relatively complex mission. I don't know. You could put a radar that's closer. I think with Veritas going, and of course Envision, the way I've seen those missions, and you've probably seen them too, there might be targeted radars, there might be other sensors really, really pulling in the chemistry of and what's going on in the clouds and in the upper atmosphere. Might be something. But I have to tell you, I've seen all sorts of flavors of payload packages for these missions. So who knows? Right? Yeah. I don't know what people will propose and when, if either of those two flavors of missions happen.
Or what about reeling out a package that goes down below the balloon, and so the balloon stays up while the instrument package goes closer and closer, and maybe you can pull it back up and cool it down and put it back down again as you need to. Again, I'm sure you've thought of this.
Yeah, well, I feel like you're reading ahead, because there are people who've thought of this, and in fact we have too. And one of the recent studies we did on a mission like this, and in fact explored that. We've done a lot of tether work, not just Goddard, but JPL and others as well. And there are a lot of complexities you can imagine of a 20-kilometer tether is a dynamic nightmare in high winds, and it has other disadvantages. As the advantage of, you could send power and data back through it. So if you could solve that complex problem, not to mention the tether that long weighs a lot if it's strong enough to be down. But people have thought about exactly that solution. There is a way to, keep, if you would trade having a balloon that's capable of going up and down with maybe that mass, which allows, it has to have tanks and fill up, and you have multiple balloons, layers, but maybe you trade that mass for the mass of a tether system. So you're just dipping a small probe down and then reeling it back up to cool down again. It is something people looked at. You are not off base there. Yeah. It is something that might be worth a trade. I mean, this is what I do for a living. You make those major design trades, and you're poking down an alley that I wouldn't rule out. Right. I think that is possible. It has its own set of challenges, and we do. You've seen it. We try to decide what missions could happen, and then we try to focus on the technologies, either internally invested or externally. And we try to work on those, and that would be something you'd have to work on before you ever bid it, because you'd have to show NASA that you know how to build that system, and you're reasonably close to understanding it can survive. And I'm not sure we're there yet, but it is one of the 2 or 3 solutions to the problem we just talked about, getting getting below the clouds in a balloon system that's being looked at and looked at more than once. So maybe we'll see that someday. I hope we see all this, by the way, someday.
Of course, of course. So what's a place in the solar system that you think is underexplored, and you think there's some interesting engineering solutions that could get us there, and it's not Venus?
Okay, you're asking a very interesting question. I think a lot about this.
I know, I can tell.
If I can only get one answer, I'm gonna answer with Enceladus. That's my answer. Give it one answer, and there's a lot of reasons, a lot of interesting things going on there. You know, it's an ocean world. We have a big set of missions going to Europa, and I think Enceladus is the unexplored territory. One of the there are other examples. I think and a lot of it's in the moons. I mean, obviously Uranus, and you know the Decadal came out with that. That mission is one of the highest priorities, the highest priority, in fact, for the direct mission, and that is unexplored territory too, with a probe, a descent probe, probably not unlike DaVinci's descent probe to go into an ice giant. But I think my other answer would really be Enceladus. There's too much going on with the what Enceladus is doing, what it's showing us. Really, you know, can you sense the ocean flying through it? Can you get a sense for the habitability? Could you even, Fraser, get evidence of life by landing or going through those plumes? Because it's one of the few places outside of Mars you can imagine life potentially being, and that is a core, incredible question you can answer. So I think that's a place that I think is important, and I spent some time thinking about that, and I think it's because of its uniqueness, it's underexplored.
Yeah, I mean, the fact that it is actually spewing this water enriched with hydrogen gas out into space, that there's got to be some way that you can just peek over the edge of the geyser and have a taste and see what's coming out of it. Unlike Europa, where it really seems like this stuff is under 10 kilometers of ice plus. In the whole how do you get under the ice at Enceladus is a non-issue because it is right there throwing into space. Well, Michael, it's been absolutely fascinating, and again, congratulations on the combo going to Venus. We're all quite excited and to seeing it launch. If people want to keep track of your work, what's the best place to do it?
Well, for DaVinci itself, you can find us online. There'll be websites, there'll be presentations, there'll be updates for DaVinci all the time. We're getting into our late phase B. Veritas too. You'll see updates for them since they launched before us. And for what I do in the studies, you can download some of those things too, and that gives people a flavor for what I'm doing. And people can always reach out to me.
Yep. Fantastic. Well, Michael, thank you so much for taking the time to chat with me today. Very exciting stuff. When you do send that probe to Enceladus, let me know. All right. Take care.
Thanks.